So can I start? Yeah, okay, great. Thank you. Okay, so good morning, everyone. Thank you for interrupting once again your sleep schedules to come in here, especially to listen to something a little bit complicated. So as you might remember, over the last couple of days in this section of lectures, we've looked at a number of different methods for approximating the ground state eigenvalue of the electronic Hamiltonian. And all of the methods that we've considered so far have one property in common. So they're all essentially Galerkin approaches. So we have some minimization problem posed on a very complicated space. And what we say is that this problem is too difficult. So instead, we're going to reduce our minimization space to something which is a little bit more tractable. So if you consider as an approximation space the set of all Slater determinants, you get the Hartree-Fock method. If you take a nice approximation in the form of these VK spaces that we introduced, you get full CI. Then we also talked about MCSEF. All of these are variational methods in the sense that they just reduce the space over which we want to solve the minimization problem to something that is a little bit simpler and easier to handle. So this final method that we're going to talk about in today's lecture, it takes a very different approach. It's not about minimization of an energy. It just considers a completely different idea in order to find, the goal is still the same. You want to find the lowest or ground state eigenvalue of the electronic Hamiltonian. But the way we get there is very different. Okay. So this is called coupled cluster, which I'm sure many of you have heard of. I took the liberty of writing down the equations because otherwise it takes me like 20 minutes or 25 minutes to actually get to these equations. So I just wrote them down here first. If you don't understand what this means, the goal of the first 45 minutes is to explain what each of these objects, which I haven't introduced, what they mean. So I've written down a complicated equation. One thing that I would draw your attention to right now is that this is not an eigenvalue problem. It's a nonlinear problem in which the goal is to find somehow like a zero of the equation. So you want to find some object, this vector that I call an amplitude vector, t, such that when you plug it into the equation, you get zero. So this is very different from solving a minimization problem. What each of these objects are in this equation, so this t, I call an amplitude vector. This capital T, I call a cluster operator. And this size 0, I call a reference determinant. So the goal of the next like half an hour will be to explain what each of these objects are. But this is really the form of the equations that we obtain in the end. Okay. So just to remind you, because this is something that we'll refer to a couple of times, just a small recap. So we saw versions of this yesterday. So if you take an L2 orthonormal basis of H1 of R3, and you define an index set, which I call here I infinity, which consists of all n tuples which you have ordered, so such that alpha 1 is smaller than alpha 2 and so on. And you don't impose any constraints. So previously we had a version of this kind of an index set where I used the subindex k. I was just imposing that these indices are less than k. Here I don't impose anything. These indices can be any natural numbers as long as they're ordered. So I use this to define an index set. And now if I consider all possible Slater determinants that I can construct from these orbitals that satisfy this ordering relation, I will get a complete L2 orthonormal basis for the full infinite dimensional space H1 of R3 consisting of antisymmetric functions. So it's exactly what we did in the full CI case, except the difference is in the full CI case, you always have finite dimensional approximation spaces. We had finite dimensional basis sets. Here, we just remove the finite dimensionality and go to the complete basis set limit. The reason I want to do this is because I would like to write this equation not in a finite dimensional space, but in the infinite dimensional H1 antisymmetric R3n space. Okay, so for that, I need all of these infinite dimensional objects. Okay, so this was the recap. Then here is where we really start. The first thing that I would like to do is to explain what these objects, these cluster operators are. And in order to do that, I'm sure many people already know this, but in order to do that, the first object that I need is something called an excitation operator. Typically, these are defined in quantum chemistry using second quantization, but I'm not going to do that. I'm just going to define them without referring to second quantization rules. And if I want to do that, then the first step is I need to introduce the notion of an excitation index set. And that's what I've done over here. So we start by taking some j, a natural number between 1 and n, and then we define the excitation index set nj. as a collection of two rows of j numbers each. So we have j numbers at the top and we have j numbers at the bottom. And we impose certain conditions on these numbers. The conditions we impose are that the numbers at the bottom have to be between 1 and n, and the numbers at the top have to be strictly larger than n. And of course, as always, we impose a certain ordering. We make sure that A1 is smaller than A2 is smaller than A3 and so on. And this set, for a fixed j, we refer to this as the excitation index set of order j. And of course, what I can do is I can define this excitation index set for any j between 1 and n. And I can take the union of all of these. And this gives me an index set that I call n, which I refer to as the global excitation index set. And once I have this set, so it looks like a weird definition, but people who know excitation operators can kind of recognize the key features here. But once I have this, then I can define excitation operators. And I'm going to do this in the following way. So you take some j between 1 and n. You take some excitation index mu in this excitation index set nj. You assume that it's of the following form. So since it's in the excitation index set nj, it has to be two rows of j numbers each. You will have j numbers at the top. You will have j numbers at the bottom. The numbers at the top, the numbers at the bottom are between 1 and n. And the numbers at the top are strictly larger than n. Okay. And then corresponding to this particular choice of index, I define the excitation operator x mu, which will be a mapping from L2 antisymmetric R3n to L2 antisymmetric R3n. So the difference between this space and this space here is that here we impose some additional regularity. So functions here have to have square integrable first derivatives. Here we don't say anything like this, okay? So a priori, I'm just defining excitation operators on a much bigger space. So how are they defined? So this is defined through its action on the n particle basis, which is the set B wedge. So the idea is that if you can define the operator on the basis, and you know that the basis is an L2 orthonormal basis, then by linearity, you can extend the action of this guy to any wave function in L2 antisymmetric R3n. So all I have to do is to explain to you how this guy acts on elements of the basis. And how does it act on elements of the basis? So the action is the following. So given some determinant psi nu in this basis, we define actually, I think I'll just use the other side because the definition is a bit long. Yes? Sorry? Oh, yeah. Yeah, so I was very sloppy here because I didn't explain what anything means, but here this should be anything which is perpendicular L2 orthogonal to this guy. And also in H1. But I will get to this. Yeah, you're right. I didn't write this. But this is supposed to be any wave function, in fact, which is L2 orthogonal to your reference determinant and which has enough regularity so that you can actually take the duality pairing. That's any function in H1 which is L2 orthogonal to the psi 0. Okay, so I'll leave that here because it's nice to have the equation to look at while we progress. Yes?
So how do you justify that it has to be orthogonal to psi 0?
Why does it have to be orthogonal to psi 0? When we derive the equations, we will see. I mean, in principle, the point is, if you take something which also has a component of size 0, then you will recover exactly the energy. And if it's orthogonal, then it has to be 0. So this equation is only satisfied if this guy is orthogonal to size 0. If there is a size 0 component, the size 0 being the reference, yeah. Okay. So given some psi nu in our basis set, we set, now I can write what it is. So the excitation operator x mu acting on psi nu takes the following form. In two cases, it is 0. And in one case, the notation I use is that it is equal to psi nu alpha, psi nu A. Okay, so this is the case if, write down now, L1, L2, up to Lj is not a subset of mu1, mu2, mu. If there exists an AM in A1 to AJ such that AM belongs to mu1 up to mu n, and this otherwise. Okay, so what does this mean? So I should probably explain what that is. Where psi nu A is the determinant in the wedge constructed by replacing orbitals phi L1, phi L2, and so on until phi Lj, used to define psi nu with orbitals phi A1, phi A2, and so on up until phi J. Okay, so this is a complicated way of writing this, but the idea is very simple. So basically,
Shouldn't the psi A mu depend on L as well?
yeah, it depends on L, but I mean, there's only enough space to. So for me, the reason I wrote an A here is because that's what you add to that. So now the output is something which still has some orbitals from the original, and then it has some new orbitals which depend on the indices A. But yes, of course, you've removed some orbitals which depend on L. That's true. So there is a dependency on L, but yeah. Yeah, there is. I mean, in principle, it depends on what the mu here is. And the mu, of course, depends on the A and the L. So yeah. If you like, I can put a small L here or a L here as well, but yeah. But you're right. Okay, so the idea here is rather straightforward. You have an input Slater determinant psi nu, which means that this guy will be of the following form. So this guy will be made from some orbitals. So it will be like phi nu1, wedge product phi nu2, and so on up until some phi nu n. So it's made from n orbitals. You have an excitation operator x mu with an excitation index of this form. So all you do is you go through the excitation index, you check out all of the L indices, the bottom ones, you see whether these are present in the construction of your input determinant. So is there a new one, is there like a L1 which is present here? Is there an L2 which is present here somewhere or not? And then what you do is you replace all of the ones which are present here with orbitals which have the corresponding A indices. So you will replace the orbital phi L1 with phi A1. You will replace the orbital phi L2 with phi A2, and so on and so forth. And if at some stage you realize that you cannot do this, then you just set the output equal to 0. So there are two situations in which you can't do this. So one is the situation where you are going through your index L1, L2, L3, and you see that one of them is not present in the input determinant. So since you can't do the replacement, you just set everything equal to 0. The other situation is that there is already some orbital phi A1, A2, A3, one of them is present in the input determinant. In this case, you also set the output equal to 0 because you have an antisymmetric function. So if you repeat the orbitals, you just get 0. And the final situation where you actually get something is where you can do this replacement. You can replace all of the orbitals phi L1, phi L2, phi L3, and so on with phi A1, phi A2, phi A3. Okay, one comment, actually, never mind. If someone asks, then I'll mention it, but yeah. So that's the basic idea. This is how we're defining excitation operators. So this, by the way, for people who are familiar with second quantization, so what you're basically doing is you are annihilating these orbitals, L1, L2, L3, and you are creating the orbitals A1, A2, A3, and so on.
Sorry, I'm a bit confused because so it seems to me that your A's are the occupied orbitals and the R's are the virtual orbitals. Is it vice versa?
No, it's
But
so
they belong to 1 to n.
so L are the occupied and A are the. Is it the other way around usually?
Yeah,
Okay.
No. It's just that okay.
Okay.
Fine.
Yeah. Okay.
Yeah, the rows are.
Yes. Yeah, exactly. So that was the comment that I didn't want to make. So the other problem here is, okay, there is this one thing that I brushed under the carpet, which is suppose you have an orbital like you have a wave function which consists of something like phi 2. Okay, I can't cook up a good example. What would it be? Yeah, okay. Yeah. So you have this. This is your input determinant, and you apply the excitation operator with index mu equals. So you replace 2 and 4 with say 11 and 12. So you take x mu with this, except maybe I should just do this example once so people are familiar, comfortable with this. Okay. Okay, so example. So I have a very simple one. So let's take psi 1 to be phi 1, phi 2, phi 3, and phi 4. And we take two mu's. So we take a mu 1, which is you replace the last two orbitals with, say, 11 and 12. And then the mu 2 is you take orbital number 2 and 4, and you replace this with, again, 11 and 12. So what happens if I now consider x mu 1 acting on psi 1? So for the first guy, this is really straightforward. All that'll happen is you go through the bottom indices, you see there is a 3 here and a 4 here, you just replace it with an 11 and a 12. So you just get that this is phi 1, wedge, phi 2, wedge, phi 11, wedge, phi 12. So this is immediately clear. For the second one, there's a small issue, which Eric pointed out, which is, in principle, I have to do exactly the same thing. I have to identify the 2, and I have to identify the 4, which of course exist, and replace them with 11, 12. But if I do that, you see that I will get a phi 1, wedge, phi 11, wedge, phi 3, wedge, phi 4. And here I have a problem because this guy is not an element of my basis set. It's not an element of my basis set because the indices are not ordered in an increasing fashion. So actually what I have to do is I have to replace this with this. So I have to flip the order of the indices. And what will happen is that I'll get a minus sign. So up to a plus or minus sign, that's something people have to be careful about, but otherwise, I think it's more or less clear what the idea is. So that's why I wrote here, where did it go? Yeah, here. So I wrote that this is the element in B wedge, which is constructed by replacing the orbital. So we make sure that it's really a Slater determinant in the basis set that we've defined. Okay. So one more remark. So I had this originally as a definition, but since we're low on time, I will just write it as a remark. Oh, actually, I'll keep it as a definition. I just won't explain it very well. For any excitation operator x mu, we denote by x mu dagger, which will also be a mapping from L2 antisymmetric R3N to L2 antisymmetric R3N, the L2 adjoint. And we say that this is the excitation operator. So basically the idea is that, okay, here when we define excitation operators, what we're doing is we're replacing occupied orbitals. So we are replacing these guys with indices less than n. These are always called occupied orbitals with virtual orbitals, with orbitals that have indices greater than n. And de-excitation operators do exactly the opposite thing. So in some sense, they're inverses. They're not exactly inverses, but they're almost inverses of excitation operators. They replace virtual orbitals with occupied orbitals. So they look for orbitals which have indices greater than n, and they replace them with orbitals which have indices smaller than n. Okay. So now we have this. I'm not going to write the full complicated definition of how this is defined. And instead, I'm going to move on to a theorem. So what are some basic properties of these objects that I've defined that are called excitation operators? So I have 5 of them, starting with very simple and then getting a bit complicated. So the first one, which is really nice, is that if we have any two excitation operators, x mu and x nu, then these commute. So all excitation operators defined this way, they commute. And it's the same for de-excitations operators, also de-excitation. One thing that I would like to comment on here is that the reason that these guys commute is because we only consider excitations from occupied to virtual. Sometimes in some couple cluster theories, people also consider excitations from virtual to virtual or from occupied to occupied. If you include excitation operators like this, then the excitation operators will not commute. And this is really a nightmare. So that's why most people, at least from a mathematical point of view, it's really nice to restrict yourself only to occupied to virtual excitations, because then these guys commute. And that makes life a lot easier. Okay, so this is comment number 1. I have it here. Then the second comment, or the second point of this theorem, is related to the question of why introduce excitation operators in the first place. What's the reason that we want this complicated construction? So the reason for this is that these excitation operators, they give us a very nice way of parameterizing our basis set B wedge. So you remember I introduced this n-particle basis set B wedge for the full function space H1 antisymmetric R3N. And using these excitation operators, we can parameterize the elements of the basis. And this is very useful. So this is my second comment, or second statement of the theorem. So if I define psi 0 to be the Slater determinant, which is constructed from the first n orbitals, then B wedge, our basis set, is nothing else than psi 0 union all possible excitation operators acting on psi 0. So basically, any determinant in our n-particle basis set can be constructed by finding some excitation operator and applying it to this reference determinant psi 0, which is the one that is constructed from taking only the first n orbitals. Okay. Then the third comment, which I again brushed under the rug, is the fact that x mu as a mapping from L2 antisymmetric R3n to L2 antisymmetric R3n is linear and bounded. So I don't know if this was clear from the definition, but you can show it without too much trouble that each one of these excitation operators as a mapping from L2 to L2, they're bounded. And the reason for this basically is that they maintain kind of, in some sense, orthogonality. So they map Slater determinants to Slater determinants, and all Slater determinants are L2 orthonormal. So that helps us. No, I don't think so.
Take one, you can only create the orbitals or the range as just no.
So what is true is that here, if you write this, for a given mu and a given nu, there is exactly one alpha such that this is not equal to 0. But here, if you have a full wave function with an infinite number of determinants, then the output can be an infinite number of determinants. But in fact, this is all you need in order to prove L2 boundedness. It's not very complicated. And this is also true for the L2 adjoint. It's a bounded operator. Okay. And then the final comment, so I compressed things a bit. This one is the one that's really not so nice to prove, but it's a fantastic result for our purposes, which is the fact that x mu and x mu dagger, not only are they bounded linear maps from L2 to L2, they are in fact bounded linear maps from H1 to H1. And this is really not obvious. So I'm not going to talk about the proof of this at all. I will talk a bit more about this kind of a statement in a little bit when we have another theorem, but this is not an obvious result at all. And the reason for this is that we define these excitation operators by their action on an L2 orthonormal basis. So they map L2 orthonormal functions to L2 orthonormal functions. But now if you start measuring things in the H1 norm, these Slater determinants are not H1 orthonormal. So it's not really clear that if you apply an excitation operator to an arbitrary wave function in H1, you will really get something which is still in H1. And it gets trickier than this when you continue. Okay. So the consequence of this is, so this theorem that I've written before, and in particular the second statement, that any wave function, so this implies from the previous theorem, that any phi, which is in H1 antisymmetric R3n. Actually, did I write H1 antisymmetric R3n or? Yeah, okay, let me write it this way and then I'll see if anyone complains. Can be written in the following form. So we know that we can expand such a function in the basis set B wedge. So that means I can write this as some coefficient times the reference determinant size 0 plus a summation over all indices mu in n, and then here I have a C mu and X mu and the size 0. So basically I'm using this fact that this basis set B wedge can be represented by all possible excitation operators acting on the reference determinant. And if that's true, that means that I can represent a wave function phi as an infinite, so as some reference determinant with the coefficient plus an infinite weighted summation of excitation operators acting on psi 0. Okay.
Here you have I infinity for mu, and here you have n.
Okay, yeah. So I should have an n here. Because the excitation operators, the mu I always take to be in n. I'm sorry, I have too many index sets. And is there any other I infinity? No. Okay. Yeah. Okay. But this statement is a little bit hard to interpret because question is the series summation mu in n C mu X mu convergent or not? So you see here you have an infinite weighted summation of excitation operators acting on the reference determinant. And this begs the question then, this series, when I write it this way as an infinite weighted summation of excitation operators, in what sense is this a convergent series? Does it define something which is a mapping from L2 to L2? How do you make sense of this? So this guy is known as a cluster operator. It's just an infinite weighted summation of excitation operators. Now here, each one of these excitation operators is indeed a mapping from L2 to L2, but it might not be completely obvious that if you take an infinite weighted summation of them, this will also be a mapping from L2 to L2. Yes. Here, it's completely clear because you're applying this exactly to the reference determinant. So you know that you get determinants which are, which are L2 orthonormal. So if you want to look at, for example, the L2 norm of this guy, you will just get summation C mu squared. So everything makes sense. This is completely obvious. But nothing stops me from applying such a cluster operator not just to the reference determinant, but to an arbitrary wave function. Because this is just, I can also define, I don't have to apply excitation operators only to the reference determinant. I can also apply them to other objects. And in general, we do that. So if you want to extend the definition of this infinite weighted summation of excitation operators, then you have to ask the question, in what sense does this series of operators converge? And if it does converge, what does it converge to? Does it converge to an operator that acts from L2 to L2, from H1 to H1? What's going on? But I agree that if you're only applying this to size 0, then it has a meaning. And yeah, it's okay.
Well, my question is the convergence of the series of operators from where to where?
Yeah. Okay. So this was the question. And then, yeah. Okay. So now we have this long proposition. The first, okay. So this is how I have written it. So there are 3 statements that I will make. So the first one is the following. So one bit of notation maybe. So I will frequently write, if I have a series like this, I will frequently write this as C of, well, in this case, C. Or if I have a summation that looks like a T mu, X mu, then I might write T of T something like this, okay? So it's just a shorthand notation. The key thing here is that in order to define this infinite summation, what I need are the weights. So I need a vector, which is going to be in, for example, so this guy C will be in, for example, little L2 of n. And once I have this vector, then I can define the corresponding cluster operator as just an infinite weighted summation where the entries correspond to the entries of the vector. Okay, so proposition. This is what I wrote down. So for every square summable sequence T mu in n, and this is the vector. So by square summable, I mean that it's in little L2 of n. So it's in the set of sequences indexed by this excitation index n such that the sequences are square summable. So for any such sequence like this, there exists a unique bounded linear operator which I'm going to call capital T. Which will be a mapping from L2 antisymmetric R3n to L2 antisymmetric R3n. Such that T is equal to summation mu n Px mu with series convergence in the L2 antisymmetric R3n operator norm. Okay. So this is statement number 1. Yeah. So that if I have a sequence which is square summable, and I construct a corresponding cluster operator out of this. So for example, here, if I assume that the C mu are square summable, then the cluster operator, which I can define by taking the series, is a bounded linear mapping from L2 to L2. And these two are equal. So this cluster operator is equal to this infinite summation in the sense of convergence in the operator norm. So that, I guess, answers your question. Furthermore, so this, by the way, so this guy, typically we call it cluster operator generated by the vector T. Okay, so this is statement number 1, and this has an addendum, which is, moreover, there exists a constant beta greater than 0, which depends only on the number of electrons n, such that the little L2 norm of this vector T is less than the operator norm of capital T as a mapping from L2 to L2, which is in turn less than this constant beta times the little L2 norm of the vector n, of the vector T. So in other words, in some sense, if you know what the norm of this vector is, you know everything about the corresponding cluster operator. You have a precise bound on the operator norm of the cluster operator. It's bounded below by the L2 norm of the vector, and it's bounded above by a constant times the L2 norm of the vector. Okay, so this was statement number 1. then this has a generalization. I mean, it's basically the same statement. It's not that difficult to see, but I'm going to write it in a little bit of a different way. There are any questions, please ask. Okay, so this was statement number one. Second statement in this proposition is, I'll just write over there. So in particular, for any wave function phi in L2 antisymmetric R3n, there exists a corresponding unique cluster operator T, which depends on phi. Such that if phi is of the form, okay, wait. So there is something I need to put extra. So this is in L2. Intersection size 0 perp. So you take any wave function which is L2 orthogonal to the reference determinant. Then for such a wave function, there exists a corresponding cluster operator T of phi, such that if phi is of the form, it's some T mu x mu of size 0, then T of phi is just taking the same coefficients and multiplying them with the excitation operators. And here again, series convergence in operator norm. And there exists a constant beta greater than 0 such that the L2 norm of phi is less than the operator norm of T of phi, which is less than beta times the L2 norm of phi. So all I'm saying here is that in the first statement, we said, okay, if you give me a square summable sequence, then I can define a corresponding cluster operator, and this guy will be well defined as a bounded linear mapping from L2 to L2, and I have series convergence in the L2 operator norm. The second statement says, okay, instead of giving me a square summable sequence, if you give me a wave function, which is in L2 and which is orthogonal to the reference determinant, then again, I can define for you a cluster operator corresponding to this wave function. And this cluster operator also has series convergence in the operator norm. It's a mapping from L2 to L2, et cetera, et cetera. So in some sense, there is a correspondence between square summable sequences and cluster operators, or between wave functions that are L2 orthogonal to the reference and cluster operators. There's a one-to-one correspondence like this. Okay. And final thing, so just to save time, same types of statements apply, or I shouldn't say same, but similar to the adjoints. So we don't really need this right now, so I won't talk about this too much. But similar types of statements apply to adjoints. Okay. So this was the first main thing about cluster operators, that we know how to define them. We know what sort of mapping they define. We know it's a bounded linear mapping, et cetera, et cetera. Okay, but this is not good enough, because if I now go back to the original equation that I wrote before, you see here I have a cluster operator. This is acting on a reference determinant size 0. So I know that, well, okay, I also take an exponential, but let's not worry about the exponential for now. A priori, if I use the result that I've just shown you, I know that this guy is in L2. When I apply this cluster operator, I will also get something in L2. But here I'm applying the Hamiltonian. So the result that I have is not good enough because I cannot apply the Hamiltonian to an arbitrary function that is in L2. I need to have stronger regularity. I need to show that if I start with the wave function, which is in H1, and I apply the cluster operator, then I get something which is in H1 so that I can apply the Hamiltonian to this guy. It's not enough to be in L2. So we need a stronger version of a statement like this. Okay. Yeah. So this is then the theorem. Yes? Yes, yes, yes. Please ask. No, there's been no. Yeah.
Infinite space.
Yes.
So if phi corresponds to the true exact solution to the Schrödinger equation.
Yes.
So the orbitals that you are using, so because you know in the HVZ theorem we talked about, so if I just adopt the one electron point of view, like I saw Schrödinger, the Hartree-Fock equation, so there are the like this spectrum with the eigenvalues, and then there is the continuum. Something that always puzzled me is like, do you need this continuum in the one electron picture to have access to the exact solution to the Schrödinger equation or not? So is it included in I infinite, or because I suspect there might be some subtleties?
So, okay. So to answer your question, this is something that Yvon asked me at some point. I don't know whether it's the case or not because, okay, so let me go on step by step. So basically, your comment is that if you take, for example, the Fock operator and you take all of the eigenfunctions of the Fock operator, these do not form a complete basis. They only span a certain part of, okay. Here, when I do the I infinity and when I consider a complete basis, that means by definition that I have to take more than the Hartree-Fock eigenfunctions. I have to take the part which is not included in the Hartree-Fock eigenfunctions. It has to span everything. And I know that if this is the case, then all of this works, and I should be able to reach the ground state and of the Schrödinger equation and approximate it well if I have the complete basis. I don't know if it might be the case that the particular solution to the Schrödinger equation doesn't require you to pull orbitals from outside the eigenfunctions of the Hartree-Fock. I mean, I don't know. This is like an.
What I know is if you have a finite basis set, like when we use atomic orbitals, the nuclear cusp, that's what exact property, you don't get that one. So if you do regular CI and finite basis set, you never will get that one.
These are all, yeah, I agree,
You
but
will approach it, but you will not.
yeah, but that's kind of the point. All of these statements are asymptotic. What they really say is that if you tell me that you want to be within an epsilon distance of some wave function, which in this case is the ground state, then I can tell you that there exists some case such that if I take enough basis functions, I can approximate the target to an accuracy of within epsilon. That doesn't mean that you have exactly the target wave function. It just means that you are epsilon close to it. You can tell me whatever epsilon you like, and with enough basis functions, I can get epsilon close to what you want.
So here in all this discussion, phi is supposed to be an approximation to the exact solution of some.
So here, I don't impose anything on phi. Right now, phi can be any wave function, which could have an. Okay, when I say an infinite number of determinants,
Yeah, that's
what I mean is that there is not a finite number of determinants that I can use to represent phi. So it's infinite in the sense that if I pick a finite number of determinants, it's not exactly equal to phi. There's always something a little bit missing. So when I write this notation, yeah.
So the bound solutions to Hartree-Fock, there will be an infinite number of them, but still you don't cover the entire.
Yes.
Okay.
What is for sure the case is that you can find functions in H1 of R3 such that if you minimize the distance between states spanned by the Hartree-Fock eigenfunctions and this guy, you will never get close. So it's completely in the orthogonal.
Thanks.
You say even the complete basis sets, one particle basis set, the Fock operator will not give you
A complete basis. There is a little bit of a subtlety here because you could do a couple of things. You could either say Okay, can we discuss this immediately afterwards? Because one thing you can do is you can say, okay, this is a nice point, but let me just do it briefly. So you can take a collection of single particle function spaces. So something like this, yeah, k greater than or equal to n. So you take a collection of these. You take a collection which is dense in H1 of R3, right? And in each one of them, you do a Hartree-Fock calculation, in each one of them. If you do a Hartree-Fock, if this is dense in H1 of R3, and in each one of them, you are doing a Hartree-Fock calculation, every time you do a Hartree-Fock calculation, you get k orbitals. And if these guys are dense, doing a Hartree-Fock calculation is nothing else than just doing a unitary transformation of the orbitals. So if you do an infinite number of Hartree-Fock calculations in this dense sequence of subspaces, then in this way, you will get something which is dense in H1 of R3. So we can discuss, yeah. At least this is what Antoine also told me at some point, so I think it's true. Okay, so finally I get to the major theorem, which is now the following. So we had a proposition about cluster operators, and now we have a theorem. And this is the thing that we really need, which is the following. So for any phi in the orthogonal complement, the L2 orthogonal complement of psi 0, intersected with H1 antisymmetric R3n, the corresponding cluster operator which I use the notation T phi. So this guy, we know it's defined through this relation. So from the previous proposition, we know that it is a priori defined as a mapping from L2 to L2. It's defined as a series which converges in the L2 operator norm sense. But what we can show is, in fact, that if your phi is in H1 antisymmetric R3n and it's in the complement of psi 0, then this guy is a bounded linear mapping from H1 to H1. So in other words, if you start with a wave function, which is not just an L2, but it's an H1, in fact, and you look at the cluster operator, then this cluster operator is not only a bounded linear mapping from L2 to L2, it's in fact a bounded linear mapping from H1 to H1. So this is exactly the sort of result that we wanted to have, because we want to be able to apply the Hamiltonian to cluster operators acting on some kind of a reference determinant. However, I should warn you, warning, no series convergence in H1 operator sense. So in other words, I can of course write T phi as an infinite summation of excitation operators. This series converges in the L2 operator norm sense, but it does not converge in the H1 operator norm sense. It's only the final limiting operator, this cluster operator T phi, which is a mapping from H1 to H1. Okay, so this was comment number 1. Second statement, T phi is also bounded from H minus 1 to H minus 1. So you can go from H1 to H1, and you can also go from H minus 1 to H minus 1. This is important because you see here, my Hamiltonian, it takes as input something which is in H1, and it gives me as output something which is in H minus 1. And here again, I'm applying a cluster operator. So I want to make sure that I can go from H minus 1 to H minus 1. This result is actually not that difficult, because once you have H1 to H1, you can use duality arguments to get H minus 1 to H minus 1. And finally, T phi dagger. is also bounded from H1 to H1. But not from H minus 1 to H minus 1. Okay. Oh, and one more comment here for this guy, which is the following. So I'll just write it here. So there exists another constant, which I call beta h, because now we're talking about the H1 norm greater than 0, such that if the H1 norm of phi is less than or equal to the operator norm of T phi as a mapping from H1 to H1, which is less than or equal to this constant times the H1 norm of phi. So it's exactly the sort of result that we had over here, just with a different constant. Okay. And I think that's pretty much everything we need, but I would like to take a minute to talk about this. So this result is, in my opinion, the most important technical result in what we understand in the mathematical analysis of coupled cluster. It's by far the most important result, because this is the result that allows you to state something like this and give it meaning. And this was proven basically by, so I think the fundamental ideas were there in the first paper by Reinhold Schneider, but he did everything in finite dimensions. This version, which is a super technical, so it's one paper that basically proves this. The entire paper is dedicated just to proving this result because it's really highly non-trivial. So this was done by a PhD student of Reinhold's. His name is Thorsten Roveda. It's a paper in ESIM, and it's, yeah, just proving this result. And I think it's by far the most important technical result in the analysis of coupled cluster. Okay.
And it was recent, no?
About 10 years ago, 10, 12 years ago. I mean, the question is, okay, so you could also ask the question, why do we care? Why should we care about a result like this? So the reason is that when coupled cluster was first introduced, it was introduced within the framework of full CI. So you treat full CI as the ground truth. So this is what the true solution is. And then you view coupled cluster, truncated coupled cluster as an approximation of full CI. But as mathematicians, what we were interested in, or some people are interested in trying to answer is, what is the relationship between coupled cluster and the true solution to the electronic Schrodinger equation? Okay, there is a relationship between full CI and coupled cluster, but can you also relate coupled cluster to the exact electronic Schrodinger equation? And when you write something like this in infinite dimensions, this is supposed to give you the relationship between the exact Schrodinger equation and the exact coupled cluster method. And then everything that we do in practice, this truncated CC or full CC or whatever, these are all just discretizations of this equation. So it gives you like a framework in which you can analyze all of the discrete coupled cluster methods. Okay. So one, yes? Yes, yes.
Regarding point number 1 of your proposition.
Yes.
So you said that the sequence T has to be square integrable.
Square summable, yes.
Are any sequence T coming out of this equation square?
Yes, they will all be square summable because H1 is just a stronger norm than L2. So by definition, anything here will be square summable, meaning that everything here is still true. But this gives you more. It tells you that if, in addition to the sequence being square summable, the sequence is such that the corresponding wave. So you see, what is the sequence? The sequence is this guy. Yeah, okay. The sequence is this guy, right? So you know that phi is in H1. That means phi is in L2. That means if I take the L2 norm of this, I will just get the sequences. Yeah, I will just get the square, the L2, little L2 norm square. So this is the sequence. But when I say phi is in H1, then I want something more than square summability. It's
So the solution of this equation is not unique. And are all the solutions square summable?
So here I write that we seek a vector which is in a V, which is a subspace of square summable sequences. This subspace is exactly, I will define it in a minute, but it's exactly constructed in order to make sure that any wave function which is constructed from this T is in H1. The solutions to this equation are not unique.
Yes.
They're not unique.
Each solution.
Yes.
That's
Each solution will be square sum. Each solution will be square sum. It will be even more than square summable, but in particular, it will be square summable. Yes. Yes. Okay. So this is then the comment. So you see here, in the original statement that I wrote down over here, we talked about sequences which are square summable. We talked about wave functions which are square summable. Here, this is the theorem that we really need. We talk about wave functions which are not just square integrable, but they are in H1. So what we would like to do now is, actually, before that, just a small comment. If you look at these theorems, this first proposition that I wrote down, you'll notice that the way I define cluster operators, I have two options. Either I say that for any vector, I can define a corresponding cluster operator, or I say for any wave function, I can define a corresponding cluster operator. So when I write down the coupled cluster equations, I somehow have an option. I can think of cluster operators as either being generated by wave functions, or I can think of cluster operators as being generated by these amplitude vectors. So we have one of two options on how we view things. Most of the time, people think of cluster operators as being generated by sequences, by amplitude vectors. And this is the usual way that it's done in most papers. So that's the approach that we're going to take. We're going to view cluster operators as being generated by sequences. But this result, you notice, is a stronger result than just taking square summable sequences. The square summable sequences result is this one, which just gives us L2 to L2 boundedness. Here, we want more boundedness. We want something from H1 to H1. So in fact, we cannot take as our set of sequences square summable sequences. We need to take a smaller subspace, which imposes more condition on these sequences or these vectors. So that's what I would like to do next. I would like to introduce a subspace of the space of square summable sequences, which allows us to use basically this theorem. So definition. We define, as you probably see from the left there, bold V as a subspace of L2 of n. And it's defined in the following way. So bold V consists of all sequences T of the form T mu, mu, and n belonging to L2 of n such that if I construct a corresponding wave function from this sequence, then this guy belongs to H1. Okay, so it's only those sequences in little L2 for which if I construct a corresponding wave function as an infinite weighted summation of excitation operators acting on the reference determinant, I will get a wave function which is exactly in H1. Okay, so this allows us to leverage this kind of an a statement. This space, so I'm not done with my definition yet, is in fact a Hilbert space. And it has a very natural inner product, which is if I have any two sequences T and S in V, then I take the inner product between the wave functions constructed from S and T. So I have two vectors, T and S, in this Hilbert space. The inner product, the V inner product, is defined as follows. You construct the corresponding wave functions from these sequences, and then you just take a look at the H1 inner product. And we know by definition that each one of these wave functions will really be in H1, so this inner product is well defined, et cetera, so everything makes sense. Okay. Yes? Yes, exactly. That's a very good point. So all of these constructions, especially when you start talking about sequences, everything depends on the choice of the reference determinant. So yeah, that is completely true. The reason for going through the wave function dependency of the cluster operator is because this allows you to have different reference determinants in some sense. But yeah, you're right. Everything here depends on the choice of reference determinant. If you change the reference determinant, everything will change. Yes?
Just to conclude, I don't understand. Over there, like for that result, we don't have any hypothesis on the coefficient T's.
Yeah, actually you do. You have hypothesis in the fall. Well, you have them indirectly. So look here, I say phi is in H1. So this means that if I write phi in the form, it's a summation over mu of some T mu, X mu, psi mu, then if I take the H1 norm of this has to be finite. So it indirectly gives you a condition on the coefficients.
So why we define that set instead of just the hypothesis?
Because then we can think of everything. We can think of cluster operators as being defined through sequences. So we view cluster operators as, you feed in an input sequence and it gives you a corresponding cluster operator. Otherwise, if we could stuck with this, then we would have to think of cluster operators as being defined by wave functions, which are in this space. It's fine. You can do it this way as well, but in my opinion, the notation is nicer if you rely on sequences, because then you can just do like T of vector T, and then it's clear what this means. Sorry, can you say? Yeah, the correspondence is exactly that. If you take any vector here and you construct a corresponding wave function, this will exactly be a wave function here, which is L2 orthogonal to this guy. So for any vector T there is a phi like this. And for a phi like this, there is a T here. Is that true? For every phi, there is a T here? Okay, I have to think about the second statement, but yeah, for the first one, yes. For every T here, there is a corresponding phi of this form. And yeah, I guess for every phi here, there is a corresponding vector here. So yes, there is. It's just a way to look at coefficients instead of looking at wave functions. Okay, so I'm running out of time, so I'm going to speed up a bit. So I really don't know. Okay. So this is done. This is done. Okay, so now instead of going through a bunch of other results, I will just quickly write down a proposition which gives us the last tools that we need. We'll just combine everything. So let T be in this set V, then exponential of T is a bounded linear map from H1 to H1. And from H minus 1 to H minus 1. So if I take a T, which is here, that means that my cluster operator corresponding to this guy is a bounded linear mapping from H1 to H1 or from H minus 1 to H minus 1. And that means that I can take the exponential And this will also be a bounded linear mapping, either from H1 to H1 or from H minus 1 to H minus 1. So this is, you just take the power series definition of exponential and you see that everything works. Okay, so this is statement number one, which is very obvious. Second statement, maybe a bit less, but I don't have too much time to go into this. So let phi be an arbitrary element of the function space H1 antisymmetric R3n, such that the L2 inner product of phi and the reference determinant psi 0, this is exactly equal to 1. So this is called intermediate normalization in quantum chemistry. Then, if this is the case, there exists a p vector in the coefficient space V such that exponential of t acting on psi 0 is exactly phi. So it's a representation theorem or representation theorem. Yes. This is really obvious, actually. It's not that complicated. Just to give you an idea, the reason is that basically, you know, from just the representation that you can write any phi like this as identity plus some cluster operator C acting on psi 0. So this is just the CI kind of linear expansion. And then what you do is you notice that the log of identity plus C, you can write this as an expansion. And the reason that this expansion works is because these excitation operators are nilpotent. So it's a terminating series. So here you will get something like a summation m minus 1 m plus 1 c to the power m. And then you know if you just take the exponential of this guy, you will get immediately that exponential of t acting on psi 0 is exactly identity plus c acting on psi 0. So it works quite easily. The only, I guess, difficult thing to do would have been to prove that this logarithm can be defined as a series like this, but since everything is nilpotent, you know, it's a terminating series. Yes, for any one of them. Okay, so here the construction I've given, like the definition of the excitation operators is such that they assume that psi 0 is the one which is constructed from the first n orbitals, because that's how I define my excitation operators. But you could reorder your orbitals to make some different orbitals, your first n orbitals, and then the same construction works. The only thing you need is for this overlap to be non-zero. As long as the overlap is non-zero, you can always intermediately normalize your wave function, and then you can represent it as an exponential. Of course, the thing is, we see this really in the numerical analysis, that the bigger the overlap, the better is your coupled cluster approximation. So if you have a very tiny overlap, of course, in principle, the exact equation has a solution, but when you do discretizations, you get horrible approximations. And you really see it in the constants and in the error estimates that you develop.
So your overlap being one, you mean like non-zero?
If it's non-zero, then you can always divide by the right number, so you get one. But yeah, basically you need it to be non-zero. But if you want this to be true, then it has to be exactly equal to 1. If you want this to be true. Otherwise, there will be like you'll have to divide by something here. But yeah.
You must pause the ground state all the time.
Yes.
And so if I take if I start with oh no, psi 0 is like an excited state.
Yes. Actually, so I will talk about this a little bit, but I don't know how much time I have. So let me just tell you, this equation, in fact, is in principle, all of its solutions correspond to the excited eigenvectors, which are intermediately normalizable. Yeah. Okay. All right. So now we're almost ready to see that equation. There's just one final calculation that I will do briefly. So I will be very sloppy and not do it in the weak sense, but it's just to give you the idea of where this equation comes from. Okay. So thanks to those results, now coming back to the exact electronic Schrodinger equation. So we know that H applied to the ground state is exactly equal to E star GS multiplied with the ground state. Yes, this is just the definition of the ground state. If this ground state is intermediately normalized, we don't know if this is true or not, but usually if you can find a good enough reference determinant size 0, which has a non-zero overlap with this ground state, then you can indeed intermediately normalize this. And to find a good reference state, which has non-zero overlap, people tend to do Hartree-Fock because it's in some sense the best kind of rank 1 approximation of the ground state. So we assume that this is intermediately normalized. It's not an unreasonable assumption. So that would imply that H exponential of T GS star. So the fact that it's intermediately normalized means that there exists some vector T, which here I call T star GS, such that H exponential of T star GS psi 0 is equal to E star GS exponential of T star GS psi 0. So I just plug in the fact that this guy is intermediately normalized. So it has an exponential parameterization. And now I have the brilliant idea that I should apply. Okay, so notice that this now makes sense, right? Because here I have an exponential, which I know is a mapping from H1 to H1. Here I have my Hamiltonian, which I'm treating as a mapping from H1 to H minus 1. So everything is okay. And now here I can apply the exponential of minus T star GS on both sides. And if I apply the exponential on the right-hand side, I just get an E star GS to the size 0. And notice that this is also allowed because I know that the exponential of a cluster operator is also a bounded linear mapping from H minus 1 to H minus 1. So I can indeed apply it on the left. And if I apply it on the left, here I get a similarity transformed Hamiltonian. And on the right, the exponential with the plus sign cancels out with the exponential on the minus sign. And now I notice that on the right-hand side, I only have a reference determinant. So this means that I have one of two situations. I can either take the inner product or the duality pairing of this guy with some excited determinant. And if I do that, I get exactly 0. So if I take kind of the inner product or the duality pairing with an excited determinant on the left and on the right I have the reference determinant. I know that all of the determinants are L2 orthonormal, so I will just get 0. And if I take the same thing with the reference determinant, I will get back, because of L2 orthonormality, just the energy. Yeah, and these are the equations that we have on the left. So the goal is, as I said, to find the cluster, to find the amplitude vector T star GS, such that this equation is exactly equal to 0. And if you have that, then you will get the energy just by evaluating this expression. Okay, so this is exactly what I wrote down before. We want to find the vector here such that here everything is 0. The only difference between this equation and this equation is that here, is that here I am testing one by one against all excited determinants, and here I'm testing against everything at the same time, but it's really the same thing, the excited determinant. So when I say that phi tilde here is L2 orthonormal to psi 0, that just means that it can be represented in terms of these excited determinants. So it's really the same equation. All right. So in the last 10 minutes, I will just re-express this equation in a form. Yes?
So the first step on the second line, you took like C0 from the position over there.
Yeah.
Okay.
So you mean going from here to here? Yeah. You mean going from here to here, right?
Yeah.
Yeah. The fact that psi star GS is intermediately normalized means that there is some vector t in this coefficient space V such that I can express psi star GS as exponential of t acting on psi 0. And intermediately normalized, meaning that this condition is true. Meaning that the overlap of this guy with psi 0 is exactly equal to 1. Yes?
Maybe you can set that. So are you going to tell us what property survive when you truncate the cluster operator at some point? Or you don't ask?
I was, so what properties? I was only going to write down, honestly, I was just going to write down what the discretizations correspond to and maybe talk a bit about, why it's a more complicated problem. But I don't think, honestly, I will have time to do that, but we can, have a conversation. Yeah, there's one more. Sorry, I didn't hear that at all.
Here it says find T,
Mhm.
that's for any phi tilde.
Yeah.
Okay.
Exactly. So you want to test with any possible phi tilde, and in practice, what you do is you don't test with all phi tilde, you just do one by one with the excited determinants. Okay. So I will do two things and then maybe some hand waving stuff, but yeah. So in practice, so these are, or what I wrote down here are the exact or the continuous coupled cluster equations. They're exactly equivalent. I mean, you can show this, they're exactly equivalent to the electronic Schrodinger equation in some sense. But of course, we don't solve these equations. So what do we do in practice? Well, in practice, what we do is we don't look for a vector t in this infinite dimensional Hilbert space V. What we take is a discretization, a finite dimensional subspace. So typically we put here a VH, which is some finite dimensional subspace. So it could consist of indices which correspond only to single or double excitations, something like this. And then we don't satisfy this equation. So we will have a TH in a finite dimensional subspace. So we put an H everywhere. And then we don't satisfy this equation for all possible wave functions, which are L2 ortho, normal to the reference determinant. Instead, we only satisfy this equation for all x mu psi 0. And this is then for all mu and the reduced I don't even remember what notation I was using, but yeah, it was NJ, I guess. So it's in fact union of NJ, J going from say 1 to M, something like this. So we don't satisfy the exact equation. We only make sure that if we test against some excited determinants, we are equal to 0. And we make sure that the amplitude vector that we use to construct the cluster operator only is constructed from some amplitude, non-zero amplitudes. Okay, so typically that's what's done. Yes?
Also, when you take the scalar product with its size 0, and then you replace with phi tilde, because I don't remember if we have a result that if we apply it through to size 0, we can span all the L2.
Yeah. I had it somewhere. Yeah, exactly.
Okay, so
Yeah.
that's,
Yeah, exactly. Okay. So what I would like to do right at the end is to show, I mean, when you look at this equation, this looks incredibly complicated, but there's a way to at least write it in a simpler form. So what I'd like to do is just to end with doing that so that people recognize, I guess they already know this, but in fact, this problem is not really that complicated. So what we do is the following. So we define, it's just a different way of writing the same problem, but the advantage of this is that it's much easier to analyze mathematically if you write it this way. So we define the coupled cluster function f as a mapping from this coefficient space V to the dual of the coefficient space V. And this is defined as follows. So f of some input vector t tested against some output vector s is nothing else than you take summation over mu and n, s mu, x mu, psi 0. So basically you take the output vector, well, you take the test vector S, you construct the corresponding wave function that you would get from taking this test vector S. And then on the right, you will have, oh, this is sloppy. I'm just inverting the order, so I have the same thing on the left and on the right. Okay, and here you test against exponential of minus t of t, h exponential of t of t, psi 0. And here we now have a duality pairing. Okay. So the coupled cluster function is a function from the coefficient space. So it takes as input a coefficient vector, for example, t, and it's a mapping to the dual space. So that means I need to tell you how it acts when you test it against some element in V. So you have an input vector t, and you have a test vector s. And if you want to compute the action of this, so what you do is you construct from S the corresponding wave function as an infinite weighted summation. From T, you construct this exponential of minus T, H exponential of T, and you apply it to psi 0. Now what you have on the right, so you start with something which is in H1, you apply cluster operators, you get something which is in H1, you apply Hamiltonian, you get something which is in H minus 1, you apply cluster operator, you still get something which is in H minus 1. So the right-hand side is in H minus 1, and here on the left you have something which is in H1 because the sequence S is in the set V, or the space V, okay? And the reason for writing all of this down is because then if I call this equation 1, then 1 is equivalent to the following. So find T star or T vector, whatever you want to call it. Maybe there I said T vector, so I'll say T vector here, such that for all S in V, it holds that S tested against f of t is equal to 0. And here we have a V plus V star. So this equation over here is in fact nothing else than finding the zeros of the coupled cluster function. The coupled cluster function is a mapping from an infinite dimensional coefficient space to the dual of the space. And all we would like to do when we say that we want to solve this equation is to find the zeros of this guy. So it's like a root finding problem in infinite dimensions. And people who do truncated CC know that it's exactly a root finding problem, right? So that's all it is. Can I take organize? Yeah. So a question to the organizer. Can I take just 5 more minutes to wrap up? Is that okay? Okay. Yeah, thank you. Okay. So a few comments about this. So now, I mean, okay, so from the analysis point of view, or, from a mathematical point of view, the sort of questions we would not like to answer are the following. So does this equation have a solution at least? If so, is the solution unique? And then if we don't solve this equation, this continuous equation, which we never do, if we solve some kind of a discretization, do these discrete equations have solutions? Are these solutions unique? And if the answer to all of this is, yes or maybe sometimes, can we find some kind of error estimates that relate the discrete solutions to the exact solution to this equation? So for the continuous equation, so this equation over here, which I've written in this form over here, this is the exact equation, you can show that there is almost never a unique solution. In fact, every intermediately normalized eigenfunction of the electronic Hamiltonian, so you take any intermediately normalized eigenfunction of H, it will generate here a 0. So you can show that every intermediately normalized eigenfunction corresponds to a 0 of the coupled cluster function. So the number of intermediately normalized eigenfunctions you have indicates the number of zeros you will have. So typically you never have uniqueness. But this is good news because at least it means that if you have a ground state eigenfunction which is intermediately normalized, you know that a solution exists. Second question is this solution unique or not? At least locally. So you know that if you're in a ball, nothing can go wrong and you can, yeah. And the answer to this is yes, it is unique. This goes through implicit function theorem and inverse function theorem. You can prove that the ground state solution, if your ground state eigenvalue is simple, then the ground state solution here, the ground state 0 is unique, locally at least. For the truncated equation, there is no nice correspondence between intermediately normalized eigenfunctions and zeros of the truncated equation. You can have lots of zeros which don't correspond to anything physically, and it's, in my opinion, it's not really possible to say a priori that if you have a truncated equation, from knowledge of the exact eigenfunctions, I can say this, and this about the solutions. You completely destroy the nice structure here, the nice correspondence between the eigenfunctions of the exact Hamiltonian and the zeros of this guy when you do the truncation. So this doesn't work. All we can say is that if the truncation is rich enough, meaning that you truncate high enough, you have enough orbitals, etc., then there will exist a ground state 0, and this will converge to the exact 0 of the continuous coupled cluster equations. Yeah. However, on the question of how many zeros there are for the truncated equations, you should stick around for the next 2 lectures on coupled cluster, because Fabian will talk exactly about this, how to quantify the number of zeros you have in the discrete coupled cluster equations. Okay, yeah, I guess that's pretty much it. I didn't get to talk about the analysis at all, but at least I think we were able to arrive to a good point of seeing what the CC equations look like. Okay, thank you very much.
Very much.